back to Hidden in the Stars. In this episode, we're covering a pretty awesome and extremely important topic, the cosmic microwave background. On May 20th, 1964, almost exactly 60 years ago to the day, two radio astronomers named Robert Wilson, seen here on the right, and Arnold Penzias, seen on the left, made the discovery of a lifetime. They were having fun as astronomers do, just pointing a radio telescope at different places in the sky, when they registered an unknown signal that they couldn't attribute to anything. Unknowingly, they had just uncovered one of the wonders of the universe, the cosmic microwave background. When this accidental discovery was revealed, it probably came as no surprise to astronomer Ralph Alpher, who, while researching the Big Bang theory, had already predicted its existence in 1948. Finally, the nearly 13.8 billion-year-old secret of the cosmos had been exposed. According to the European Space Agency, the cosmic microwave background is the remnant of the first light that could ever travel freely throughout the universe. About 380,000 years after the Big Bang, the universe was in an extremely hot, dense soup-like state of particles. Although the universe was no longer doubling in size, 90 times in a hundredth of a billionth of a trillionth of a second, or 10 to the negative 34th power, it was still expanding, just much more slowly. As the universe expanded, it became transparent. Even through this newly transparent space, the cosmic microwave background is still invisible to the human eye. This is due to its extremely freezing cold temperature of 2.725 degrees above absolute zero. We know from the equation temperature Fahrenheit equals 9/5 times the quantity of temperature Kelvin minus 273.15 plus 32 that it is equal to negative 454.765 degrees Fahrenheit. This single temperature of radiation, equals 2.725 Kelvin is derived from the equation found for the specific intensity of the cosmic microwave background. That equation reads as the intensity of the frequency equals the quantity of 2 times the Planck's constant times frequency cubed over the speed of light squared times the quantity of e raised to the Planck's constant times frequency over the Stefan-Boltzmann constant times the temperature of radiation, all subtracted by 1, all raised to the negative first power. Even though we can't see it, it's everywhere in the universe. If the cosmic microwave background was able to be detected in the visual part of the electromagnetic spectrum, it would look like a glow that's uniform in all directions. Also known as the CMB, the cosmic microwave background is a form of radiation. It has very small fluctuations in temperature of plus or minus 1 over 100,000 degrees. An interesting bit I found from Professor Stephen Perinaud on the size of the universe says, at the time of the beginning of the cosmic microwave background, that the volume of the universe was 1100 cubed, a billion times smaller, around 90 million light years in diameter for the region that is now within our light cone or horizon. Almost like an extremely old snapshot, the CMB allows us to look into the past. It tells us the ages of some of the oldest stars, as well as the composition of the universe. Here, we see an anisotropic map of the cosmic microwave background. We really didn't go into these too much, so I'll be brief. The 4 colors seen stand for the variables energy, temperature, and density. The colors to look for are red, magenta, blue, and turquoise, respectively. The graph shows the inverse and direct relationships between those variables. Energy can be solved as change in energy equals mass times speed of light squared. Temperature can be solved as change in temperature equals heat over mass times speed of light. And density is mass over volume. If I'm not mistaken, you can save all of these equations for the same variable m, mass. Setting them equal to each other, this would make the entire equation energy over the speed of light squared equals heat over the temperature times the speed of light equals the density times the volume of the cosmic microwave background. However, the critical density of radiation has already been solved for, equaling 1.88 times 10 to the negative 26 times h sub 100 squared kilograms over meters cubed. This was equated using the dimensionless measure of the value of the Hubble constant. This accidental discovery was absolutely essential in leading most astronomers to believe in the Big Bang. Some scientists would even say that the cosmic microwave background confirms the Big Bang theory, further strengthening the theory of inflation, too. Without this marvelous new knowledge, we may still be lost looking past Oort clouds in the interstellar medium for answers. The future for science looks bright pertaining to the cosmic microwave background. According to JamesWebbDiscovery.com, with the James Webb Space Telescope, scientists will be able to study the CMB because of its sensitivity and ability to observe in the infrared spectrum. They go on to say, we can learn about the early universe's magnetic fields and how they affected the formation of structures in the universe. Using these new tools and technologies, perhaps we can be even more precise in pinpointing where all this radiation came from. Maybe then the truth of the origins of the universe will unfold. I hope you enjoy. Do you have a topic? Drop a comment below. Thanks for tuning into this episode on one of my favorite topics, the cosmic microwave background. Come along and join us on a journey through the cosmos. Catch you next time here at Hidden in the Stars.